Okay, so I'll explain to you now the statement of Green's theorem. Remember from last time, the idea is that if you have being a conservative vector field is the same as the fact that if you take a closed loop, right, F conservative is the same as work being 0 on closed loops. So what that means in particular is that for Green's theorem we have to work on the xy plane. Later we will see how to generalize this. But so what that means is that if you take a vector field if you take a closed loop, right? Imagine this is like a curve which you're traveling this way. In general, the work along this curve will be non-zero because in general the vector field is not conservative. So what we want to do is find the work along C, okay? And what Green's theorem says is that the work along this curve, again, this just means work done along the curve C, is the same as a double integral. So this curve encloses some region R. This is why you need the statement to talk about closed curves, because otherwise if you have a curve which is open, then it does not enclose any natural region on the xy plane. But what Green's theorem says is that if you have a closed curve, then the work along the curve is the same as a double integral over this region of something. And so this is what we have to find out. And like really it's like a very important statement, although I'll tell you some of the consequences later. But philosophically this is saying that if you want to know something that's going on the exterior, right, like this is, if you think you are living in this two-dimensional region in space, you're a tiny insect living here, you have your own world, right? This is saying that what's happening at the border, right, can be determined by the information on the interior, and you can also use it the other way around. So what's happening on the interior is to a large extent also determined by what's happening on the border. Okay, and again, I'll say more about that in subsequent videos, but for now let's just try to see why that's true. So the question is, what should we put here? And in order to figure that out, let's just work the case of a rectangle. So case so when you're a small rectangle, what do I mean by that? So here you have x, y. Let's say you take a rectangle, and here's the point x comma y, and this rectangle has one side of length delta x, and so if this one has a side of length delta x, this gives you x plus delta x comma y. And let's say it has another side of length delta y, and so this would be the point x plus delta x, y plus delta y, and this would be the point x comma y plus delta y. Okay, so we have this rectangle, and again for these problems, it's a closed loop, right? And we're going to move counterclockwise. The point of this orientation is that that way, as you move along this curve, you see the region enclosed to your left side, to your to the left hand side. So let's try to understand what the work should be. Again, we want to compute. Z is a small rectangle. It is broken into 4 pieces. Call them C1, C2, C3, C4. Okay? And so what we want to understand, as I said, the work is additive. So the work along the entire rectangle, which is C, is just the work along the first piece plus the work along the second piece plus the work along the third piece plus the work along the fourth piece. Okay? And let's do it this way. What was the formula in general for work? Remember that in general, let's see, this will be easier. Yeah. Remember that the formula for the work is the integral of the velocity times the force dt from time 1 to time 2, right? Now, velocity, right, is dr dt. So another way to write the work, which is actually a bit more useful in this occasion, is to say that work is just the integral from again this dt cancels this dt, so you just get v dot dr from the initial position to the last final position. So the initial position of the position vector to the final position of the position vector. And here dr, you should think of, because we're on the plane, dr is just dx comma dy. Okay? And f, because we're on the plane, it has one component, one horizontal component, and one vertical component. So let me just write it like this. Okay? So to illustrate what the main idea is, let's do the work along the curve C1. So the work along the curve C1 would be the integral from the initial position by this formula. This is just, at the end of the day, you can, this is like an explanation of the fact, but eventually you can just know what the result is, so you don't have to worry really about the proof. But I think it's useful to know at least where this comes from. So the work would be the integral from the initial position, which is xy, to the final position, which is x plus delta x comma y, okay, of f dot drs. So f1 dot f2 dot dr, okay, which is dx dy. But here's the thing, you should think of this dx as a change. Notice that dy would be the change in y along this curve. But the point is that this curve being parallel to the x-axis is not changing in height. So this dy, which is the small change in height, is 0 in this case because the segment is horizontal. Or if you prefer, if this is confusing you a little bit, you can think about it in terms of the original formula. And in the original formula, the velocity vector along the curve 1 would just be the vector I, right? So when you do the dot product, the point is that only the first component survives. So you get, what I'm trying to say is that really this is just like an ordinary integral in x. So this becomes an integral. So you don't need to keep track of the second coordinate because it is not changing. So it's like an integral from x to x plus delta x of f1 of xy dx. Okay? And, or let me, yeah, well, doesn't matter. Let's call this x naught, y naught, x naught, y naught, x naught, y naught, so that is less confusing. So the initial point is called x naught, y naught. So this is like an integral from x naught to x naught plus delta x. Okay? So this looks a little bit better. And now I'm going to do the horrible thing that's which is the following. I'm saying this rectangle is very, 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 very small. So it is so small that I will pretend that nothing happened, meaning that this first component of the force did not change at all. Okay, so I will assume that this is constant. It's almost a constant, and if that's the case, then this integral is approximated by, well, if it's always almost a constant, then you just need to understand the value at the initial point. So it's just approximated by f of x naught, y naught, times the length of this interval, which is just delta x. Again, this is a horrible thing to do, but which we will do. So the work is approximately, the work along the first curve is approximately equal to the value of the vector field at x naught, y naught. Sorry, this is the first component of the vector field x naught at x naught, y naught times delta x. Okay, and why am I doing this? Let me explain what happens with the third step, okay? Because the other one is essentially the same. So for the, the vertical curves are analyzed in basically the same way. So for curve number 2, right? Sorry, curve number 3, the one that's upstairs. The work is really, again, if you use this formula, the work is the integral from, notice that you're starting here, so you put x plus delta x, y plus delta y, to the endpoint, which is x naught, y naught. The endpoint is x naught, comma, y naught plus delta y. And you're taking the dot product between f1 and f2 with dx, dy. And again, the point is that this is 0 because there's no change in height. So this is 0 again. So you just find that you need to do the following integral from x naught plus delta x to x naught of f1 dx. And again, I'll do the horrible thing of saying that this is essentially the same as one of the constant, that this is approximately constant f1, okay? And so I will approximate it, say, by, let's see, I'll approximate it by the value at one of the endpoints. So let's approximate it with, I'm approximating it, say, with the initial endpoint every time. So let me approximate it with this one. times the length of the interval, which is, now notice the length of the interval is minus delta x. Another way to think about it is that if you prefer in terms of velocity, the velocity vector here is minus I, and here is I. So this is why this one gets a sign. And so if you want, let's see, well, yeah. Okay, yeah. Let's keep it this way. So if you want, what I'm saying is that the work, what we find is that this is the work along the curve C3. So combining these two results, what we find is that again the total work had to be the addition of these of these four works. But so that means that the work along C1 plus the work along C3 is what? Well, or is approximated by what? Let me just do it here. So the work along C1 is approximated by F1 x naught, y naught, delta x, and the work along C3 is approximated by minus F1 x naught plus delta x, y naught plus delta y times delta x. Okay? And so really you can factorize delta x here, and so you get f naught x naught y naught minus f1 at x naught y naught minus f1 at x naught plus delta x y naught at plus delta y, all of these times delta x. Okay, and now what we have to do is understand this term, and for that I'll do the Taylor expansion. As I was saying, the work along the first curve and the third curve can be approximated by this difference, which since both have delta x, I just factorized it, and then we just have to understand the difference between the function. Again, f1 is the first component of the vector field, so we have to understand the difference between that component when evaluated at these 2 points. And for that, I'll do Taylor's theorem. If you remember, I mentioned Taylor's theorem once during class, but what it said is that the following. If you want to understand the value of a function at some point in terms of another point, right? So here I'm comparing the value of this function at this corner versus that corner, then it's just approximated by the value of the function at the point you care about. In the usual Taylor theorem, you would have the first derivative, right, times the length of the interval. In this case, there are 2 derivatives, so you would put the first derivative of f1 with respect to x times the length of the interval. So the length of the interval in the x component is x naught plus delta x minus x naught. So let me just multiply, write it like that. Plus the partial derivative of f1 with respect to y times the length of the interval, or the length of or the difference in y values. So it's and there are more things, but again, we don't care about those. This is like a linear approximation. And so simplifying a little bit, this is saying that this is can be approximated by f1 x naught y naught plus f1, the partial of f1 with respect to x times delta x, plus the partial of f1 with respect to y times delta y. Okay? And so if you substitute that in there, what this is saying is that the work along the first curve and the third curve is approximated by what? Well, it's approximated by this thing minus that thing. So when you subtract it, when you replace f1 this with this expression that we just got, right? Notice that this term is being cancelled by that term, and so you just get minus f1 delta x times delta x minus f1 with respect. You get minus the derivative of f1 with respect to x times delta x minus the derivative of f1 with respect to y times delta y, and all of this was multiplied by delta x. Okay, and so what that means is that really the work can be approximated. So this can be approximated by when you do the multiplication, you approximate this by minus f1 delta x times delta x squared minus f1 with respect, minus the partial of f1 with respect to x times delta x squared minus the partial of f1 with respect to y times delta x delta y. And we're getting close to our end result. Here's the thing. Delta x times delta y is basically the area of this rectangle. Which, let me call it delta A. Now, the point is that this delta x squared, again, like the full proof, you need to be more careful about this, but the idea is that actually this can be disregarded, basically because you can only, when you do double integrals, for example, you can integrate only once with respect to each variable, and this will eventually correspond to doing like an integration, and so this makes sense for a double integral, but you cannot do on a double integral like dx. Or another way would be to say that delta x is like delta x squared is sufficiently small that you can ignore it. But at the end, again, this is just like a heuristic for why the argument should be true. But it's just that there's not like a useful geometric interpretation you can make of this term, because you cannot integrate twice with respect to x, and so you ignore this term. This is not worse than all the other things I have done so far. This is full of horrible things. So I'm just trying to say why you would have come up with this idea. And so if you believe after all this massacre what I have done, what I'm saying is that the work along the first curve and the third curve can be approximated by minus the partial of f1 with respect to x times delta A. Okay? And analogous, in the same way, what you will find is that the work is essentially the same argument. You'll find that the work done along the curve C2 plus C3 plus C4, sorry, can be approximated by. Okay, is this going to? Sorry. Ooh, good. This is with respect to y. That's why it was not looking very good. So good. Now I'm happy. And this can be approximated by the partial of f2 with respect to x delta A. So since delta A is the same thing in both cases, what this is saying is that total work along the rectangle can be approximated total work along the rectangle can be approximated by the partial of f2 with respect to x minus the partial of f1 with respect to y times delta A. Okay? And again here remember that f is f1, f2. And after you know that this is like a somewhat useful, valid approximation for very, 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 very tiny rectangles, what you end up finding is that if you have an arbitrary region in space, again, an actual curve which surrounds some region and closes some region R in space, well, what you end up doing is like cutting this region into super tiny rectangles. The point is that what I'm saying is that you start approximating the curve by rectangles where you can apply this approximation, and sometimes some segments are being counted twice, right? Because when you put two rectangles together, imagine that you take this one and this one. When you paste them together, then there's like a work which was done along this segment which gets cancelled with the work done along that segment. So in the end, like the interior works get cancelled and only the work along the exterior survives. And so what I'm trying to say, and this is a statement of Green's theorem, is that, and we'll do in the next video an example with it. Is that if F is a vector field on the xy plane, then for any curve, for any closed curve, so the more precise statement can be found on the PDF, but this is like the survival guide's version of the statement. What we're saying is that the integral, the work along this curve, right, for any closed curve C, which is here, the work along this curve, which is again, remember, f dot v dt, or f dot dr if you prefer. Right, this is the usual definition of the work. So this is T1, T2, or R of T1, R of T2. Again, this is the usual definition of the work. This, according to Green's theorem, instead of computing this integral, Green's theorem says that you can compute a double integral of this quantity. dA. So again, in the next video, again, this, well, first of all, it's like an amazing result. It's saying that like an integral, once a single integral is actually equivalent to a double integral, you just have to change what you're putting inside inside each of the integrals. And moreover, we'll exploit some of the consequences of this in a couple of videos. But for now, what I'll do in the next video is just remind you of Green's theorem, the statement, and do an example with it so that you see how this plays out in practice.